Hi, everyone. Yes, I'm happy to present this poster on behalf of our team of 6 co-authors, led by Ilaria Pascucci, and it also includes Susan Edwards, Uma Gorti, Oliver Gressel, and Takeru Suzuki. Uma and Takeru are with us here in Kyoto, and we'll be happy to answer your questions and discuss more if you wish after the talk. So this chapter actually covers both observations and theory of diskwins, and we have been focusing on a few central questions that have been raised since PP6. What is the empirical evidence for radially extended diskwins from protoplanetary disks? Do MHD diskwins primarily drive disk accretion? Do photoevaporative diskwins primarily drive disk dispersal? And how do diskwins affect planet formation and migration? And the chapter focuses on low-mass stars because that's where we have the largest body of data from the earliest to the latest phases and new advances since PP6. And I will refer you to our chapter for a more extensive review and references, because here I will only be able to give you the few highlights. And I apologize in advance if you don't see your paper reference here. It's certainly incomplete, but the chapter is much more exhaustive. So in terms of observations first, the spatially resolved outflows, since we have made a lot of progress since PP6. In PP6, we only knew about one case of a source where we had evidence for diskwins, and this is Digitau A, the Titori star Digitau A here. We had already seen a kind of onion-like structure in velocity, where this is the fastest material seen in iron 2 at high velocity. We had a lower velocity cocoon surrounding these jets in iron 2, and in H2, an even lower velocity layer encompassing these components. And then finally, with ALMA, recently there was an even slower COR flow observed around this. So this onion-like structure you see is in velocity, but also in temperature and in chemistry. And since then, with ALMA, we have been actually finding quite a number of other examples, and very spectacular ones, especially in younger sources where the jets are much stronger and the outflows are much more massive. So this is Digitau B, a class 1 source, and this is HA212, a class 0 source, even younger. And in each case, you see the jet in the middle, and you see these low velocity flows coming from the inner regions of the disk within a few tens of AUs. And what is important, so we still see this onion-like structure, and also we can measure the mass flux, and it's comparable or larger than the accretion rate onto the star. And these outflows are rotating. So this is the strongest evidence we have so far for diskwins in these objects. And we also have especially unresolved evidence for diskwins, and that is in the class 2 stars, where the accretion rates are lower and everything is fainter, but we can still see an ubiquitous low velocity component in the spectrum of the oxygen 1 line. This is an example here of CW tau. The oxygen 1 profile, you can see a high velocity component that is tracing the jet, but you can also see this low velocity component here. This low velocity component is slightly blue shifted. It's correlated with the accretion rate very tightly, and so this is strong evidence for a slow diskwind. Since PP6, there has been direct evidence that this is really a diskwind, because we see it in spectroastrometry. We can measure the shifts, even though the emission is unresolved. You can see that it's shifted slightly above, a few tens of AU above the disk surface, and in the blue shifted direction. And there's also evidence for an onion-like structure, in a chemical onion-like structure, because we see that there is a stronger iron depletion at lower velocities, for example, in this very nice paper. And so it shows that the low velocity component is coming from a larger radii in the disk than the high velocity component. And then finally, with new instruments, we've been able to spectrally resolve these low velocity component profiles, not only in O1, but also in sulfur 2, in H2, and in CO near infrared lines. And what we find is that there are two kinds of profiles, actually. Some of them you have to have two Gaussians to reproduce, a broad Gaussian and a narrow Gaussian. And I will use these colors in the following to distinguish them. And some other stars you can just fit with a single component. I call them SC, as single component, and it can be broad or narrow. And if you look at the width of them, and it seems to correlate with inclination in a way that is compatible with Keplerian rotation. And so if you assume that you're close to Keplerian, you get foot point radii that typically go from 0.02 to 5 AU. So really in the inner disk, but also going to several AU, quite extended. And we also see that the broad component is bluer than the narrow component, which means that you have faster winds. If you believe this interpretation of the width, you would have faster winds from the smaller disk radii, which is what we see on larger scales. Okay, we see this onion-like structure with slower and slower wind from larger radii. And finally, if you try to estimate a mass flux, which is hard because you don't spatially resolve the emission, but if you assume a reasonable emission size compared to the launch radii, you find that it's actually a bit larger than the jet mass fluxes are comparable. So it's quite sizable. Another new finding since PP6 is that there are some evolutionary trends in these low velocity components. Now we have a large body of data, not only for torus, but also to older regions like upper SCO. And we see an evolution as the accretion rate drops and the disk clears. So here, this is showing different kinds of profiles. So the profiles, at high accretion rate, you have a lot of these cases where you have the two components plus the jet. But as the accretion rate drops, you tend to go to this other type of profile where you still have the jet in green, but you have a single component. And then at low accretion rates and in the evolved sources like upper SCO, you lose the high velocity component altogether, and you're left just with a single component. It still has a very broad range of width, from 10 to 100 kilometers per second, but you see it behaves differently with the infrared index than in the early stages. There's a different slope with the mid-infrared. And here, this is full disks on the left, transition disks on the right. You can see that it gets narrower as the disk clears. There is also a sign of evolution when we look at the neon 2 line. The neon 2 line is a trace of hard photons because you need hard photons to ionize neon. And the low velocity component in this line only appears at low accretion rates, below 10 to the minus 8 solar masses per year. And it increases in strength compared to O1 when the index increases. So as you go from full disks to transition disks, this is the ratio of of neon 2 to O1, as a function of the slope. And you can see all these thick disks here. The low velocity component is just not detected. It starts to be in only a few sources. And as you go to transition disks, then you clearly see this component, and it becomes more and more important compared to O1. Now in the chapter, we also review the basics of the disk wind theory. For those who were not in the previous PP sessions, I'm just going to do a very brief recap. So we have two kinds of disk winds, the magnetocentrifugal MHD disk winds and the photoevaporative winds. The magnetocentrifugal ones are predominantly powered by magnetic forces which drive accretion in the disk. And this is a typical simulation from Oliver Gressel showing how the magnetic field lines are wound up by disk rotation. They break the disk, they allow accretion in the disk, but they also accelerate the material in the wind. And the final velocity of the wind here depends on what we call the magnetic lever arm parameter, which we denote as lambda. It is not the same as the mass to flux ratio in course. Be careful. It's the ratio of the specific angular momentum extracted by the wind to the initial Keplerian momentum in the disk. And it's related to what we call the lever arm, the Affen radius, but this is the important parameter that controls everything in those disk winds. And the photoevaporative winds, in contrast, are powered predominantly by stellar irradiation from X-rays from the corona of the star, EUV from chronospheric activity, and far UV from the accretion shock onto the stellar surface. And this creates a hot disk surface with a pressure gradient, and this can lift material and make it escape from the disk if the sound speed is large enough compared to the Keplerian speed, which correspond to escape radii of at least 1 to 4 AU. Inside of that, you remain bound to the disk and you have no photoevaporation. So these photoevaporative winds start beyond a few AU, and the final speed is a few times the sound speed. So I'm going to go a bit deeper into the MHD disk winds. What's new since PP6? Well, there has been a lot of work, very impressive progress with 2D and 3D semi-global and global simulations of these disk winds, which we didn't have them. And they show that MHD disk winds are a robust outcome of organized poloidal disk fields in the disk. As soon as you put these vertical field lines, you get MHD disk winds, even when the midplane magnetization is low. And there are two regimes which have been discussed by Mario this morning. The first regime is when the disk is dead, so what we call the dead zone here, due to non-ideal effects, the MRI is quenched, and so the disk is laminar. And here you can still eject the winds from the disk surface where the gas recouples to the magnetic field because it's sufficiently irradiated, and beta becomes of order 1. So even if beta is very large here, you have the thermal pressure is dominant here, there is a region at the disk surface where the densities are lower, and eventually beta is of order 1. And this was already shown by in Shearing box simulations, and now it's confirmed with these global simulations. And the second regime is the ideal MHD MRI active regime. So you expect this in the inner regions, as Mario showed this morning. For example, you will get an MRI instability, turbulence, and here you expect to have a different kind of wind that is going to be fed by these fluctuations and upflows, and this was shown by Shoichiro Inotsuka, and it's confirmed now with these large-scale simulations. Going in a bit more into the outer disk winds from the dead zone, so these global simulations have made huge progress because now they include multiple non-ideal MHD effects, so ohmic, ambipolar, and Hall effect. They include XUV radiation, they include thermal chemistry. I'm putting here a few references. This is really beautiful work, and just to remind the people who are a bit old like me, I mean, you've heard about these old models where we had a beta midplane of 1. What's the difference? Well, there are some similarities. They drive sonic accretion still with an accretion rate that is proportional to BZ. That's really important. And the key parameter is still this lambda parameter, and it still controls the kinematics and the mass flux. So this is looks familiar, but there are these notable differences too, that now you can have a massive disk because it's non-accreting in the midplane. Before, in these early models, it was accreting down the midplane at sonic speed, so you never had enough surface density to build planets, but now you can have a dense midplane to build planets, and you eject from the surface. So eject from much higher 4 scale heights with a much larger B phi, also the wound up field. So you get smaller lever arms, slower winds, more massive winds. And also you can get asymmetric winds. This is a simulation by Rios, and notice this is density. Notice that the wind is much denser on the top part of the disk and less dense there. And this is driven by non-ideal MHD. There is a poster that, by the way, in green I'm showing poster numbers that I found relevant. I'm sorry if I missed yours, but I tried to be pretty complete. And then there are also global simulations of what happens when you have these vertical magnetic fields in a transition disk. So if you have an inner hole, you will also drive accretion, sonic accretion through those inner holes, and you will have properties closer to these early models with a beta midplane of 1 or so. And it's very, very interesting to see that you can sustain steady accretion through these transition disks. Now going to the inner winds from the MRI zone. Again, here we have these new, very impressive 3D ideal MHD global simulations, including MRI. And there are two main results. First, when just look at large scale, far from the star, what you see is that this MRI disk is actually driving upflows into this thick atmosphere, but still the atmosphere is there is a braking torque, and it doesn't escape, but it falls back. So it's called failed winds. You can see they're really important here. And then even higher, above 45 degrees, here you can get an accelerating torque and a conical disk wind. So you have these two components, and the disk wind here only carries about 10% of the accretion rate, because the rest is done by the MRI and by these failed winds that accrete onto the central object. So you expect much smaller mass fluxes. And when you include the star, this is a beautiful simulation by Takasao. There is a poster on this that you can check. When you add the stellar field, you get additional contributions to outflow, like magnetospheric ejections when the stellar field lines reconnect by interacting with the disk. And you can also get a stellar wind, of course. So all of these are going to interact with the conical disk winds and probably contribute to the jets that we observe. It's clear that a very important point to keep in mind is that since it is the magnetic field braking torque that produces accretion in the dead zone disk winds, it's the poloidal field strength that is going to determine the accretion rate. And this is an approximate expression just from first principles, very approximative. You can do, there are better scalings, more precise scalings in the Le Sur chapter. But just to show you that the typical field strength that you could advect during the collapse phase could be sufficient to sustain accretion, pretty high accretion rates. But then the question is what happens later on. So the flux diffusion is really, as Mario said, is a very crucial question, because that is going to regulate the MHD disk winds and how much accretion you get. And the current results that Mario showed was that in the dead zone, there seems to be an outward diffusion in the midplane, whereas in the MRI zone, it's inward midplane diffusion. But there are many open questions still to address, like, these are still early times. We would like to know how it evolves on secular timescales. Also, what happens at the wind base, because we see these disk winds are coming from several scale heights, like four scale heights, or even more in the MRI region. What happens there? Is the flux diffusion the same, or could it be slower? And also the effect of alpha dynamos and stellar field, could that induce some cyclic behaviors? All of that is really open to research. Now, the photoevaporative disk winds, the main new result since PP6 is very nice simulations coupling hydrodynamics with heating, with the different kinds of photons, and chemistry and cooling. And here you can see an example of a simulation by Komaki showing how this produces a complex, very complex wind structure with a very hot, highly ionized wind in the middle, a neutral X-ray driven wind atomic at intermediate angles, and then at the disk surface a much cooler wind. It's more like a PDR-like flow that is atomic or molecular. The difficulty here is that the results depend very much on the adopted microphysics and radiative transfer. There are some simulations where this division here, or even these two, ends up at the disk surface. So it is extremely sensitive, of course, because the wind, these thermodynamical properties feed on the wind and vice versa. So that's really something that we need to understand better, how to do this in the most rigorous way possible while coupling to hydrodynamics. It's a very challenging problem. There's a new work also coupling the dust dynamical evolution, viscous evolution, and photoevaporation to evaluate this dispersal. Coupling with dust is really important because you expect the dust to evolve, to settle, to grow, to drift, and this is affecting the heating. For example, the photoelectric heating is going to change. The radiative, photon absorption is going to change, so you want to have a self-consistent evolutionary model. And that's also something that needs to be pursued. In terms of mass fluxes, how does that translate? In our chapter, we give a full compilation of different models in terms of the mass flux per log r as a function of radius. And here, I won't discuss all of these in detail because I don't have time, and I refer you to the chapter for a full discussion. But the takeaway message is the following. For the inner winds from the inner AU, for the MHD ones, which are not plotted here, the MRI-driven winds predict a few percent of m dot accretion for the MHD disk winds, depending on magnetization. And there are no photoevaporative winds because they are gravity bound. And this is what you see here in this curve. Basically, the mass flux plummets to 0. For the outer winds in the dead zone, the MHD models predict a flat, relatively flat curve here, where basically this mass flux per log r is of order the accretion rate. For the photoevaporative winds, it's somewhere between 10 to the minus 9 and 10 to the minus 8. This is where you can see the effect of assumptions. And there is an additional point that has not been considered before in PP6, is that these inner winds could absorb part of the XUV photons from the star. And so this could quench the photoevaporation at sufficiently high accretion rates if you have 10% of that in an inner wind. So what are the implications for this dispersal? Is it due to MHD disk winds or to photoevaporative disk winds? I heard this question this morning. So this morning we heard about scenarios where the dissipation was either purely viscous or pure MHD. And here we are showing two scenarios of first a pure where we include photoevaporation. This one is the classical scenario of pure viscous accretion and photoevaporation, but it takes into account the variation of accretion rate changing the far UV flux, and it also takes into account the effect of absorption by the inner wind. And so you see this dramatic effect here that lowers the accretion, the photoevaporative rate until relatively late stages. So you're dominated by accretion, mass removal by accretion until the late phases. And then finally, the final clearing is done by far UV-driven photoevaporation. In the second scenario in blue, there is a vertical disk field, and there is a very strong MHD disk wind, and that is dominating the mass removal from the disk until the very late stages as well, a few million years. But finally, you get photoevaporation taking over. You see when the accretion, when the mass flux of the wind, of the MHD wind drops below 10 to the minus 8 or so, you start to be dominated by photoevaporation. So from these scenarios, it seems that in the late stages, photoevaporation could still dominate, even though you have MHD-controlled accretion throughout in earlier stages. Now confronting observations with theory. In terms of the spatially resolved observations, there is a strong agreement with MHD disk winds so far, at least. You have seen already in chapter 9 these beautiful AMA observations that have detected now jet rotation in one jet here, HH212 in SIO, in the same sense as the disk, in different knots, same direction. And it implies an origin from 0.05 to 0.2 AU. And this is where we have the MRI disk winds and the star-disk interaction. So that is probably, we know that jets are coming from pretty inner, really the inner disk. And I point you to some recent reviews about jets and their origin here. At lower velocity, we have these broad conical outflows. And here, this is a map of the centroid velocity in HH212, where you nicely see this velocity gradient showing rotation. This is also seen in all the other CO outflows that have been observed pretty much so far. And the mass fluxes are extremely large, as I mentioned already. They're of the same order as the accretion rate, so it's much too large for photoevaporation. There is an onion-like structure here that is well fitted by radially extended MHD disk-wind models, and I'll point you to these papers if you want to see a very detailed comparison of these observations with an MHD disk-wind model. It works really surprisingly well. But more generally, if you look at the foot points, the lambda values and the mass fluxes, they are in line with MHD disk-winds driving accretion across the dead zone. So to show you how we derive these launch points and magnetic lever arms, this is it's actually relatively easy. So you plot the poloidal velocity of your flow here on the x-axis, the specific angular momentum RV phi on the y-axis, and these are the observed data points in all of these rotating CO outflows. And you compare with predictions from MHD disk winds. The solid curves are different values of lambda. The dashed curves are different value of the launch radius in AU. And so from each point you can derive which value you need to explain the observations. And you see that we have small values of lambda, large values of R0, and this is exactly what is predicted by these MHD disk-wind models from the dead zone. Small lambda values and large R0. Also, you can go a bit further if you have a handle on the range of launch radii, like here at digitau B, we managed to do a tomographic analysis of the flow to derive the velocity and the rotation in the different layers. We did the same in HH212 with this detailed model, and we did the same in HH30. And if you know also the mass flux and the mass accretion rate, you can check that the amount of angular momentum you remove in these disk winds is exactly what you need to feed accretion through the launch zone. And so this has been done in 3 outflows so far. So if you're interested, you can check those references. Okay. Thank you. Now, going to unresolved tracers, so the low velocity component in class 2. Are these MHD or photoevaporative winds? So here, these are predicted line profiles for the different kinds of winds. For MHD disk winds predict quite complex, broad and complex profiles with multiple components. Here I'm showing a really old, result, but it's the only one I found that had a superposition with observations that was not too crowded. But there are similar results that have been found in different, like by Weber, for example. There are also predictions for molecular lines. And also in 2 posters, you can see also predictions for different kinds of MHD wind models, but they all predict these complex profiles with often 2 components. The photoevaporative winds, they predict narrow lines for the reasons I said, that you have to be beyond a few AU to escape from the potential well. There are slight differences between EUV and X-ray driven, but yeah, they look pretty similar. So how does that compare with observations? Well, you remember that some sources have pretty broad low velocity components, sometimes just a broad component actually, that can go up to 100 km per second wide. So clearly MHD disk winds would be favored for these ones. And even those that have both a broad and a narrow component, these 2 components seem to be cross-correlated in velocity, in strength, and so we feel that it's more realistic to think that they come both from the same phenomenon, an MHD disk wind, than MHD plus photoevaporation because of these correlations. But of course, this is a matter of discussion. Now, in the evolved sources where you only have, I don't know if you remember this graph as a function of the infrared index, but when you go to the clearing disks and the low accretion rates, you end up with a single narrow component, and then those are compatible with photoevaporation, and this is TW Hydra, an example of a well-known transition disk. You can see that the black histogram is the observations. You can see that it's very well fitted. And what is interesting is that this low velocity component of neon 2 is only seen at low accretion rates, so it fits with the idea that um, that's when the inner winds become transparent to the energetic photons. Now, what is the impact of disk winds on planet formation? I'm only going to skim through the surface here because there's a lot of work, and it's a very, very important and very interesting topic that has seen a lot of advance also since PP6. It has an impact in many ways. First, it tends to promote planetesimal formation through different effects. First, increasing the dust-to-gas ratio because these winds are going to lift up the small grains, but they're going to leave the big grains behind. Typically, the maximum grain size that is entrained is about 10 microns. So that's going to increase the dust-to-gas ratio in the mid-plane and favor planetesimal accretion. The radial drift can be slowed or reversed by the gas removal and also the altered surface density distribution if you create an inner gap. There is also the formation of rings and gaps by non-ideal effects that Mario showed us this morning, and that is illustrated here in the simulation. And these vortices can lead to trapping of solids and enhance planetesimal formation. And there are more effects and several posters here that are discussing this question. There is also an impact on planet formation and migration. Again, because of this inverted surface density slope and cavity opening, you can actually slow down or revert the migration and explain the formation of close-in super-Earth and sub-Neptunes. This is a poster and paper by Ogihara where you N-body simulations where you can see these different embryos interacting and merging together. And it also leads to the formation of non-resonant systems, which is also, you can reproduce the observed orbital separations better than when you have rapid inward migration. If the disk is non-turbulent, it's totally inviscid. There are also some interesting effects with vortices, but yeah, I won't have time to elaborate. But there is a lot of interesting work, hydro simulations about that also. So just a last word about future progress. On observations, we need more of these high-resolution spectroimaging studies to really probe the internal wind structure. And there are lots of ongoing, I was really happy to see the number of posters that are showing ALMA observations of the base of these winds. There are many, many posters, several of them report rotation. There is an example here in HR tau where you start to resolve some interesting substructure in the outflow related maybe to the disk structure. There are also, with JWST, we're able now to probe the H2 component of these flows and also different atomic lines from the jets. So it's bringing us, again, a different view, intermediate temperature regime between the jets and the CO. That is going to be very interesting to study. Again, that's one example of a poster. The optical is also bringing really, really nice information. And in particular, there is one poster with a detection of O1 low velocity component from PDS 70. That is quite surprising in a way, I mean, but very interesting. So check that. We would also like, of course, to see B field. Okay, sorry. We would like, on the theory side, to expand the global simulations to see the interaction of inner and outer disk winds, which has not been studied so far because it's either MRI zone or dead zone. And it would be nice to have both of them together and see how they play out and if there are some signatures of their interactions. To go to younger class 0, 1 sources and later class 2 when photoevaporative winds may start to dominate, see how that looks in synthetic predictions, and also pursue the role of winds in the evolution of solids and planet migration. And of course, the ultimate goal is to reach comprehensive theory of the role of disk winds in disk accretion and architecture of planetary systems. So I'll just put here a quick summary of the current results that are in the chapter, and thank you for your attention and take questions.
Thank you very much, Sylvie. So you know the drill, line up, and I would encourage more junior people to come up. Don't be afraid. Ask some questions. So let's start over there.
Is that okay? Okay. Hiro Takami from ASIA. Yeah, thank you very much for the talk. But as my student is here, so I have a duty to argue against your statement about, what you say is the disk-weighing nature for the forbidden line LVC is confirmed based on Emma Whelan's observations. So there are 4 points I want to address, actually. And first, Emma Whelan studies only for 2 objects. So we definitely need to increase the samples. My student, Yuru Cho, and also Emma's students are trying to do that.
Sure.
This is the first point.
Absolutely. It's only 2 sources so far. You're right.
Okay.
Yes.
And the second point, some part of the emission could be associated with disk atmosphere rather than the LBC wind. So please have a look at Cho Yuru's poster and then Yuru Cho's poster, the PF03, the 04. And we are happy to take your criticism later.
So which one is it?
The very last one.
This one?
Yes.
Okay. Yes.
Okay. Yes.
Yes. In Emma's data, there was a shift from the. There was a spatial shift between the low velocity centroids and the disk midplane, I guess. But you're right. I mean, clearly these low velocity components, anyway, they have to be formed quite close to the disk surface because the centroids are not very large. So if they are dominated by rotation, they still have to be the base of the disk wind. So yeah, it's.
Okay, the third point is some X-wind people argue the features could be explained by, all the LBC features could be explained by X-wind model, and so including interaction with ambient gas, based on their latest paper shown at all 2023 in APJ.
Mm-hmm.
And of course, so they haven't done any simulation of the emission lines. So we might be keeping our thought open for this possibility. That's the third point. Yes. The fourth point is you mentioned some ALMA observations. But for ALMA, we usually cover younger objects. So it's very different. So maybe conditions will be very different. So between what we can see using ALMA and what we observe using optical forbidden light emission.
Yeah, that's why I separated spatially resolved and unresolved. Actually, with ALMA, we see also wind like this. Well, HL tau is a young Titori star. We also have an outflow from HH30, which is a class 2 source, and actually it's an edge on class 2, and there's been observations of veiling in that source, and it's not heavily veiled. So I don't know if you consider HH30 to be a very young source, but there is no sign of an envelope around that one, around HH30. Now, I'd like to address the point on the X-wind because I think it's an important point. So I have a slide about it. I prepared it. So if that's okay, unless Peter wants to ask, but yeah, this is what you're referring to. I mean, this is the, there have been models trying to explain these outflows by untrained material by the X-wind. And the X-wind is a model where there is no magnetic field in the disk itself, and so the inner wind is actually at a constant velocity, but it's going at 180 degrees. It's very widely open. And then it interacts freely with the envelope. So there is no thick MRI disk, it's a simple model. And then the envelope or the ambient core is swept up into a shell. And there are different models for these, numerical simulations, analytical, semi-analytical work. And the caveats with this interpretation, there are several caveats. First, the rotation that is predicted is less than observed. And this has been shown, for example, in Lopez Vasquez. I forgot to put here the De Vallon paper. They compare with the predicted rotational velocities, and they don't match. There's a second problem. It's the base radius here. This is a simulation at 1,000 years. And you can see that the base radius here is already 150 AU. That's because the X-wind has such strength even though it's denser on the axis, there's still material going off at the equator at 150 or close to 100 kilometers per second that pushes against the ambient medium, skims over the disk surface, and even in steady models, like the Liang model, you get a base radius that is about the outer disk radius. And that is not what we observe. We observe base radii of 10 AU or so, so that is something quite difficult to explain with this X-wind model. If you try to constrain that, if you want to add a disk field to pinch that, you need such a strong disk field that you will drive an MHD disk wind, actually. So that is all discussed in the chapter. There is a whole section about this, if you want. And we can talk about it together later.
Thank you.
Okay, let's, I'm going to move around this way, and let's try and keep the questions short, and so we can get through more people. Go ahead.
Okay, Yao Lun Yan, Riken in Japan. I have a question about your future prospect. You show the substructure in alpha, and we also seen previous talk about using substructure in alpha to indicate potential outbursts. Can you comment on how or could we distinguish these two phenomena?
So you are referring to
the HL tau CO that you showed here?
But you're referring to which talk?
Agnes talk on the...
Agnes talk, yes. So there are two, actually, it's still a matter of, debate, even within ourselves, whether is this due to, there are several possible origins for these substructures. One is that it's related, and that's in the poster, if you go check that poster, that it might be related to the ring structure in the disk, that the self-organization in the disks that is going to produce denser wind layers compared to others, so that could make substructure. There is another option, which is that you have episodic accretion, higher accretion at the disk surface. There is a poster showing that in the supersonic or sonic accretion layer, you can actually have sometimes fluctuations in the accretion rate when you put the radiative transfer. And this could lead to enhancements in the outflow at some times. So that's in the De Vallon paper on Digitau B. You can find a modeling of that effect. And the third possible effect is this one, which is the interaction between the time variable jet and an outer disk wind. If you have outbursts in the jets that create bow shocks, these bow shocks could interact with the disk wind, and they can also produce substructure. This is a paper by Tabon in 2018. And it produces, it can also produce, structures in the overdense structures along the alpha surface. And we think we may be seeing such an interaction in H212, perhaps.
Thank you.
There is a poster on HH30 that discusses that.
And yes, go ahead.
Ahmed Nimr from NYU Abu Dhabi. Thank you so much for the wonderful review about disk winds. My question is about MHD winds. You classify them as magnetocentrifugal. And as far as I know, most models are based on very thin disk models, basically, for disk structure. And in this case, it's really hard to reconcile how this gas can be ionized to be carried away by the magnetic field. So can you please comment on that?
Actually, the 2D and 3D simulations are not using such thin, they're not so thin. If you look at, Geoffroy can probably comment more, but they take Geoffroy, can you comment on that? He's the expert.
Right, so in this particular case, yes, most of the models published to date have an aspect ratio of 0.05 or 0.1. The one we see here is 0.05. And I should say also that we always assume that there is some sort of strong ionization due to the far UVs at the disk surface, which is enough to provide the coupling to the magnetic field lines, which then make an outflow, if this addresses your question.
Yeah, thank you so much.
Yeah. So what you're saying is that we would need to have self-consistent, fully self-consistent calculation of the irradiation of the disk surface. Yeah. absolutely.
Yes, go ahead.
Yeah, Greg Herzig, Peking University. Thank you for the fantastic summary and very clear descriptions. I was wondering about an observational take on one of the theoretical predictions that you discussed. And it seems like the non-ideal simulations of accretion from reals. Also, there's a poster from Shoji Mori. And I think even the star disk interaction from Takasawa-san, who's behind me, show that the wind comes out on the opposite side of the accretion, right? So the accretion flow is on the top, and the wind comes out on the bottom.
Yeah.
And I was wondering, it seems like that should be observationally testable, challenging because we can't see the backside sometimes.
Mm-hmm.
But I was wondering whether you could kind of speculate on whether the observations support that or not. Thanks.
Yeah, thanks for the very good question. Observationally, at least we have examples of highly asymmetric outflows, that's for sure. Like digital B that I showed, it's much stronger on one side. HH30, I didn't show it, but you can check the papers. It's also on one side. So at least that is seen. Now, about having the accretion mostly on the other side, that's where I said we need to have a way to measure this sonic accretion at the disk surface. So yeah, it would be great if there was a way to look for that. In HS30, it's difficult because it's edge-on and it's a very thick disk, so there's a dust lane. I don't think you can see you can't see the surface. But in digital B, the outflow is on the redshifted side, so if we could watch we could look for sonic accretion on the blue shifted face of the disk. Yeah.
Thanks.
Yeah, I have lots of questions about that, but I'm not the questioner, so you are over there.
Peter Voigtke, Graz, Austria. My question is about stellar wind. Isn't there also a stellar wind? I mean, these stars, these young Taurus stars are huge X-ray emitters.
Sure.
They have very strong activity. They should also have corona, etc., just like the sun. Do you know of any works that trying to combine this, or do you think it's just not relevant? I could imagine the mass loss rates cannot compete, but maybe the loss of energy, if you think about energy loss rates. So is it possible that maybe all these things get again shaped by a stellar wind?
Yeah, that's exactly. I'm sorry if the label probably doesn't show very well. I'm sorry about that. But here there is a stellar wind actually in this simulation.
And do these people actually try to have a full, consistent hydro model with a generation of a stellar wind as well?
So, well, the generation of the stellar wind is another. It's a difficult issue because you need to put some heating here, but you don't know what to put. Even the solar wind we have trouble doing. So, what in Protostars, but you can try to put some arbitrary heating here. So. Right now, the consensus is that the problem is for the stellar wind to get mass out of the star, you need to climb a very steep potential well. So you cannot get as much mass as from the magnetospheric ejections. It's much easier because you reconnect close to the co-rotation point. So you're already a few stellar radii away, so not as deep the potential well. The disk winds, again, are also easier. But you're right that it could contribute to, pushing against these field lines. I don't know if maybe Takasawa can comment. I don't know if it changes the characteristics of the conical winds, conical disk winds that are there. But definitely that is, it's really the direction to go. But the problem is how much mass flux to put in there.
Okay, we're really tight, so I'm sorry, I can only take one question. I know you've been waiting for a long time, so go ahead.
Thank you very much. Megan Ryder, Rice University. Thanks for a great talk. I was just wondering if you could say a few words about what people are thinking about lower metallicities, especially now that we know of at least one collimated jet and a handful of molecular outflows seen in the Magellanic Clouds, albeit not with this incredible spatial resolution.
Wow. I didn't think of that at all. And there is a molecular, I don't even know about the data, but you have a molecular outflow around the jet, and do you see any difference from what I showed here, or does it look similar?
I think Keith Tanaka's poster is really the one to check out for that. Anna
Okay.
McLeod has a paper on a jet seen in optical wavelengths. Happy to
Okay.
chat after. Thank you.
Okay, thanks.
Let's thank Sylvie again.